Hi, our esteemed viewers. You are welcome once again to your favorite mathematics YouTube channel, Mathematics by Abu Zainab. A channel specially created for us to unravel the mysteries behind mathematics and to tackle headlong the age-long phobia associated with the subject. Today, we are looking at a very interesting topic, a topic that cuts across several layers in the secondary school. This topic is taught first in GSS 1, then again is taught in GSS 3, and lastly is taught in SS1 mathematics. Yet interestingly, this same topic is taught in SS1 further mathematics. And what topic is this? It is number bases. Number bases is a very interesting topic that is at the core of computing. As we all know, computers don't understand the languages that we speak as humans. However, all inputs into computers are interpreted as codes, as bases. It's on this basis that computers relate with us. Number bases, very important. We're diving into today's lesson by looking at the objectives for the class. Objective number 1, we are going to define what a number base is. 2, we are going to list the names of certain number bases that are common. Then 3, we are going to give the list of digits that make up each number base system. And lastly, we are going to carry out a conversion from other bases to base 10, which is the standard base. To start with, what is a number base? A number base is a digit, a combination of digits, which a system of counting uses in representing numbers. We have several bases: base 2, base 3, 4, 5, 6, and so on and so forth. However, let's look at some common bases and their nomenclature. We got base 2, which is popular, called binary numbers. And we've got base 8, another important base called octal. We've got the all popular base 10, which is the standard, and that is called denary or decimal. Thereafter, we proceed to base 12, and that's called duodecimal. And lastly, we look at base 16, called hexadecimal. So these are the number bases that have specific names. And of course, they are not exhaustive. We have a lot of them. But for the purpose of our lesson, we are looking at these basic ones. Now, we have to understand that in number bases, it's very important to note that we cannot have a digit in its base. For example, if you're in base 2, you can never have 2 in base 2. If you're in base 3, you can't have 3 in base 3. Essentially, the digits you can have in a base is from 0 up to a digit less than that specific digit. I mean, for example, in base 2, that's binary numbers. The permissible numbers, let me use that word, are 0 and 1. In base 8, octal, the permissible numbers are 0, 1, 2, 3, 4, 5, 6, and 7. These are the only digits you can have in base 8. Always a digit 1 less than the specific base. And in base 10, which is our popular base, standard base, we can have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. You can't have 10 in base 10. Thereafter, we look at base 12, the duodecimal. Here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In lieu of 10, we introduce letters. So we have uppercase A representing 10, then uppercase B representing 11. We stop there. Again, 11, which is just a number less than 12. Then lastly, we look at base 16, and the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then again, instead of 10, we have A, B, C, D, E, and F. So we have from 9, we have 10, 11, 12, 13, 14, and 15 respectively. Again, a digit less than 16. So these are the permissible digits under respective number bases, which underscores the point that we can never have a digit in its base. Thereafter, we move on straight to the operations. How do we convert from other bases to base 10, being the standard base? So for this, we're going to look at a few examples involving several bases, all to base 10. Excuse me. Base 10. Together, we look at these 5 examples of conversions to base 10. As you can see on the board, we've got a conversion from 2 to base 10, from base 5 to base 10, another base 2 to base 10, though with decimal point. Then we have a base 12 to base 10 and base 16 to base 10. Before I go further, I must emphasize that the example 1 is specific to GSS 1. As I mentioned previously at the introduction, that this topic cuts across several layers. So I'm making an attempt to give us one example fits all. This is specific to conversions to base 10 for GSS 1 level. Example 2 is base 5, and this particular aspect is incorporated for GSS 3, in addition to knowing GSS 2. Likewise, this is called bisimal, binary and decimal, bisimal numbers to base 10 as well. So examples 1 through 3, we take care of classes GSS 1 to GSS 3. Whereas in further math, SS1, and of course mathematics SS1, we're going to have conversions of duodecimal and hexadecimal as additions to the previously named bases in junior secondary school. So let's move on into the solution. Number 1, 1, 0, 1, 1, base 2. It's very important to also note at this point that it is normal, it's ideal to always indicate the number base in which one is operating. To start with, we have 1011 base 2. The 2 has to be there. The 5 has to be there, either in words or in figures. They are both permissible. This is 2 in figures, and we have 16 and 12 in words. It's very important, except we are in base 10. So how do we solve this? We have 1, 0, 1, 1. I first attempt to blow out the digits. And the base, which is 2, I make them the superscripts here, which are 2, 2, 2, and 2. And then on the 2s, starting from my right-hand side, I start with 0 there, 1, 2, and 3. The next step in the solution will be to bring out the index. So we have in parentheses 1 times 2 power 3 plus 0 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0. Now, it's very important, again, I emphasize here, the common mistake that students make is to always assume 2 to the power of 3 means 2 times 3. That's not the case. 2 to the power of 3 means 2 times 2 times 2, which makes that 8. Instead of 2 times 3, 6. We have 8. Then 2 to the power of 2 is 4. 0 times 4. 2 to the power of 1 is 2. Now, 2 to the power of 0, or any number whatsoever, to the power of 0 is always 1. No matter the number, however big or small, to the power of 0 is always 1. So then we have 1 times 8, 8. 0 times 4, 0. 1 times 2, 2. 1 times 1, 1. And in simply summing, we're going to have 11 base 10. However, base 10 has an exclusive right of either being written with the 10 as a base, or we just write 10 without anything. It's permissible only for base 10. You don't do that for other bases. You must necessarily indicate their bases. At the end of the day, we can say that 1011 base 2 is equivalent in value to 11 base 10. And that is the example of conversion from base 2 to base 10, which I believe is quite interesting and explanatory. So then we move on right away to the second example. So there we are converting base 5 rather, to base 10. So we have here 2103 base 5. Similarly, we blew out the numbers 2103. Then the base 5 becomes superscript here. 5, 5, 5, 5. And on the 5, from my right hand side, I start with 0, 1, 2, and 3. So here I have 2 times 5 to the power of 3 in parentheses, plus 1 times 5 to the power of 2, also in parentheses, plus 0 times 5 to the power of 1, plus then 3 times 5 to the power of 0. So at this stage, we multiply. 5 to the power of 3 means 5 times 5 times 5, which is 125. So 125. Then 5 to the power of 2 is 25. That's 5 times 5. Then 0 times 5 to the power of 1 is 5. And like I said earlier, 5 to the power of 0 is 1. So we multiply. 2 times 125 is 250. 1 times 25, 25. 0 times 5, 0. 3 times 1, 3. So by adding up, we have 250 plus 25 plus 3. That is 250 plus 25 is 275. Then plus 3, 278 base 10. Hence, 2103 in base 5 has an equivalent value to 278 base 10, which is pretty much similar to the first example, which I believe again is explanatory. Then we move to the third one. What makes example 3 different from example 1 is because of the decimal point. So there's going to be a slight difference in the way we solve this compared to this, which is a whole number. And we go thus. We got 11.101 is 2. So again, we blew up 11.101. Then the 2, which is the base here, becomes the superscript as before. 2, 2, 2, 2. And herein lies the difference. Before the decimal point, we have whole numbers and we have decimal or fractional parts. So for the whole numbers, we carry on as before. We have 0 here and 1 here to the left of the decimal point. Then to the right other side, we are going to have -1, -2, and -3. This is the difference between this and example 1. So we have here, again, 1 times 2 power 1 plus 1 times 2 power 0. This decimal makes no difference. We still have our plus. Then we have 1 times 2 power -1 plus 0 times 2 power -2 plus 1 times 2 power -3. There we have 1 times 2 power 1 is 2 plus 1 times 2 power 0 is 1 plus 1 times. Now, when you have a number raised to a negative index, as in this, we are going to use what we call indices, one of the laws of indices, and that's the topic for another lesson, if you stay tuned. So, I'm going to recall the law used there. We are going to have, if a raised power minus n is the index, it can be expressed as a fraction, which is 1 over a to the power of n. This is one of the laws of indices. In other words, applying this, we write this as 1 over 2 power 1. Note, the negative has been lost once the 2 becomes the denominator. Similarly, here you have 0 times what? 1 over 2 power 2. And lastly, here, 1 times 1 over 2 power 3. We are only applying the law of indices for the 2 to the negative power. Every other thing stays intact. So at this point, we multiply 1 times 2, 2. 1 times 1, 1. Plus 1 times half is 1 over 2. Plus whatever you have here times 0 is 0. Actually, 1 over 4 times 0 is 0. Then lastly here, 1 over 2 power 3 is 1 over 8. And again, we sum up. And we have 2 plus 1, 3 for the whole number part. For the fractional part, we have half plus 1 over 8. And that simply takes us to the LCM of 2 and 8 is 8. 2 in 8, 4 times 1, 4. 8 in 8, 1 times 1, 1. Hence, we have 3 whole number, 5 over 8, base 10. Therefore, 1.101 base 2 is equivalent to 3 whole number, 5 over 8. And I believe that's a bit explanatory. Now, we move on to the realm of the duodecimals and the hexadecimal. So pretty much the same, no difference whatsoever. So we have 4. We have 2, 1a base 12. We blow up as what? 2, 1, and a. 12 is the base, it becomes our superscript here. 12, 12, 12. And on the 12s, customarily we have 0, 1, and 2. So at this point, we have again 2 times 12 raised to power 2 plus 1 times 12 raised to power 1, then plus a times 12 raised to power 0. There and again, remember, 12 to the power of 2 means 12 times 12. 12 times 12, so we have 144. And 12 to the power of 1 is 12. A. Don't forget that A in base 12 means 10. Means 10. So we have 12 power 0 is 1. So we have the multiplication here to be 288 plus 12 plus 10. So if you sum up 288 plus 12, that is 300. And 300 plus 10, we have 310 base 10. And that is the conversion from duodecimal to base 10. Pretty much the same as others. And then lastly, we have the hexadecimal. How does that pan out? So, for hexadecimal, we've got 10E2 base 16. So we have 1, 0, E, and then 2. The base 16 becomes my superscript here, 16, 16, 16, and 16. And on the powers we have from here, 0, 1, 2, and then 3. So, in blowing out, I'm going to have 1 times 16 to the power of 3 plus 0 times 16 to the power of 2 plus E times 16 to the power of 1 plus 2 times 16 to the power of 0. Again, 16 power 3 means 16 times 16 times 16. And that is 4096. Whereas this is 0 times 16 squared is 256. And the letter E is 14. The value 14 in base 16 is 14 times 16. Then plus 2 times 1. So by carrying out the multiplications, we have 4096 plus 0 plus 224, which is 14 times 16. Then plus 2 there, plus 2 there. So once you have this, you sum up everything. 4096 plus 224 plus 2. And that gives us 4322 in base 10. Therefore, 10E2 base 16 is equivalent to 4322 base 10. And that exactly is how you convert from whatever number base to base 10. They utilize basically the same approach. And with that, we come to the end of today's wonderful and interesting lesson. I bet you had a very exciting class, much as I do. So to round up the class, we are going to recap what we have done today. We started by defining what a number base is, followed by listing the nomenclature or the names of certain given bases, which are base 2 binary, base 8 octal, base 10 decimal or denary, base 12 duodecimal, and base 16 hexadecimal. From where we proceeded to listing the respective digits that make up each number base, with emphasis that you can never have a digit in its own number base. You can't have 8 in base 8. The best you can have is a digit less. And lastly, we add the conversion from several bases to base 10. This is the class for today, which I believe you found so beneficial. Please, if you like this, stay tuned to our class by subscribing, liking, commenting, and sharing Mathematics by Abu Zainab. And please, tune on the notification button so that you'll be the first to know when we drop our next video. Our next class, we have a continuation of this topic, and that shall be the conversions from base 10 this time around back to respective number bases. You can call that reverse conversion from base 10 to others. Stay tuned and God bless. Thank you.